for the further part of this chapter. Okay. So let me explain you one more time what was calcination. Calcination, that we have chosen the ore. Okay, first we have chosen the ore, and then after choosing the ore, what we used to do? We used to enrich the ore. Okay, we used to enrich the ore. We enrich the ore, and after enriching the ore, after removal of gangue from the ore, what we do? We bring the sulfide ore and carbonate ore in their oxide form. There were the four types of ore: sulfide ore, sulfide ore. The second one is carbonate ore, carbonate ore. Okay, and the third one was oxide ore, oxide ore, and the halide ore. Okay, so what we do in the cal sulfide ore, for example, if I'm having zinc sulfide, if I'm having lead glens, okay, PBS, and other type of ore that is going to have. As similarly, the carbonate ore, CaCO3, comma ZNS, okay, sorry, ZnCO3, ZnCO3, and the other types of ore, etc. Oxide ore is like Al2O3, okay, and like Fe2O3, and halide ore is that is going to have chloride, bromide, okay, like NaCl, KCl, etc. So what we do, we need to bring this ore into their respective carbonate and their respective oxide. For this, what we do calcination. Calcination that you have written in your copy. Just I'm just revising. Calcination. What we does in calcination, we need to convert the carbonate, or like I'm using carbonate. In the absence of air, when you heat it continuously, then you can convert it plus ZNO plus CO2. Similarly, if you are having calcium carbonate CaCO3, then you heat it again, then it will consider CaO plus CO2. So in the absence of air, we heat the carbonate ore. This was calcination that we have discussed in the previous class. And what was oxidation? Oh, sorry, roasting. The roasting is that we are converting uh, sulfide ore, like I'm zinc sulfide, okay, and in the presence of oxygen, we heat it, strongly heat it, and it will give you ZNO plus SO2. Like we have PBS, when we heat it, it will give you PBO plus SO2. Now these have become in the oxide forms. Okay. But the next step is the removal of oxygen, and that is called reduction. So let's start the fresh topic of today, that is reduction. What is reduction? Reduction is removal of oxygen or electronegative element elements such as chlorine, bromine, iodine, etc. Like chloride, bromide, and iodide, etc. Okay, so if I am removing, for example, if I'm having NaCl, and if I electricity pass it to this one, okay, then after passing electricity, it get converted into Na solid and Cl2 gas is released. So this is reduction because I'm just removing the chlorine, electronegative element. So this is here we can say that reduction of NaCl is taking place. In the similar way, if I'm having ZNO and if I heat it with the carbon, ZNO with heated with the carbon, and it will give you Zn plus O2, CO2. So this is reduction. Removal of oxygen is called reduction. Removal of oxygen is called reduction. Okay. Everybody understood in the class?
Yes, sir.
So please note it down. Noted?
So, what have you written after NaCl aqueous solution? Then
Electricity. Electricity. NaCl aqueous. And then it will give you no. No, it should not be aqueous. It should be in liquid state. Sorry, you have to write it liquid. If it is aqueous, it will give you different product. Chloralkali process will be there. So write it liquid. And it is in molten state, and when we pass this electricity to it, then it will gives you Na solid plus chlorine gas plus this one. Okay, so this is reduction. What we are doing reduction. So next step, what we do is we have converted the carbonate ore into oxide form. We have converted the sulfide ore into oxide form. Oxide ore is already in oxide form, and halide ore, we need to remove this halogen, this chlorine, bromine, iodine. So this is called reduction. Now we need to bring the metals out of their oxide form, out of their halide or chloride form. Okay, got it? Noted, everybody?
yes, sir.
Yes, sir.
Should I move further? Okay. So let me explain you further. Here are the metals, like I'm just writing the series here. This is potassium, then sodium, then calcium, then magnesium, then aluminium. Okay, then chromium and manganese. Okay, and then carbon. This is carbon. I'm just writing carbon here. Okay. Okay, I'm just writing only C for carbon. And this one is zinc, iron, tin, lead. Okay. Then I'm just writing here hydrogen, then copper, then silver, sorry, then copper, then mercury, then silver, then gold, then platinum. Okay, got it?
Yes, sir.
So these two are the free metals. You know very well that these are the free metals. They can exist in the native state. So they don't exist in the oxide form. So this is a native state. So we are not going to we directly refine these. Okay, they are already in the native state. They are not in the oxide form. So here you see that these copper, silver, and mercury may exist in Ag2s form. This Hg can exist in HgS form, and this Cu2s copper can exist in Cu2s form. Got it? So these metals you can get the metal from this one by simple roasting. By simple roasting. Okay. And here you see that I have written carbon here, but in the reactivity series that you have seen in the metals and non-metals chapter and the displacement reactions, so that series does not contain carbon, but I'm just writing here carbon because you can, in this metallurgy, we need those elements, more reactive elements, okay, because we have this table of metals only, okay, and here is carbon. Carbon is a non-metal, so we are not just putting the non-metals here. But for your assumption and for your better understanding, I'm just placing the carbon at their position so that you can understood that carbon is more reactive than zinc, iron, tin, and lead. Okay. So, and in order to prefer, if we need to give the preference that which things you will like to use in the reduction, a metal or a carbon. So carbon is cheaper and easily available, so you will use carbon. So I'm just placing here these metal oxide, this if it is exist in the form of ZNO, if it is existing in the form of Fe2O3 or Fe3O4, and if it is SN2SNO or SN2O4, okay, and this is PbO if it is existing in this form. So these oxide can be reduced with the help of carbon. So this can be reduced by carbon, and by carbon we called it smelting. What we called it is smelting. Smelting is reduction with carbon. Okay, got it? And you see that these two metals are above the aluminium. So these, if the oxide of this is Cr2O3 and MnO2, if they are existing in this form, their oxide can be reduced with the help of aluminium, the above metal, okay, because they are more reactive than carbon, so carbon cannot be used here. So this is, we considered it reduction with aluminium, and we called it, what we called it, alminothermy. Okay, the reduction with aluminium is called alminothermy. thermy. Okay, aluminothermy. And these above metals, like if I'm having Al2O3, magnesium oxide, calcium oxide, or if I'm having NaCl, CaCl. So if these metals are present, so these are highly reactive metals. So these metals are reduced by electrolytic reduction. Electrolytic reduction. Okay, please note it down. First, make this table, then I'm going to explain you further. Reduction with carbon is called smelting. Note it, to make this table. Done? Done, everybody? Done, everybody in the class? Tejasvi, Shweta, Chobita, Ashwin, Adil, Faizan. Ashwin, it's
Done, sir.
nobody is responding. And like, look that I'm only teaching.
Yes, sir.
myself. Done? So if I'm saying that how these metals can be reduced by simple roasting. Look at this. This is very important. If silver exists in CO2 form, when you heat it in the presence of oxygen, that is considered to be as roasting. When you heat it, so it will get converted into AgO plus SO2. And on continuous heating, this Ag2O. If Ag2O is continuously heated, then it will gives you simple Ag plus O2. Okay. So by simple heating, you can convert this one Ags to, you can get Ag solid. Similarly, this Ag2S, HGS, when it is heated in the presence of oxygen, then it will get converted on heating. It will get converted into HgO and then sulfur dioxide. And this HgO on further continuous heating, and it will HgO. When you heat it continuously, then it will get converted into Hg plus O2 gas will be released. Okay, got it? And similarly for this Cu2O, here you have to, this when you heat it, it will get converted into Cu2O plus SO2. But here you need to keep in mind, if you are having this Cu2O alone, then you need some reducing agent. Then you need some reducing agent. Let me explain you here, dear students, that if you are heating something, okay, if I'm saying that if you are heating a calcium carbonate, Cu copper oxide, and this copper oxide, when it is heated alone, if you are having only copper oxide Cu2O and you heat it, it will not give you Cu. For example, previously you are having HgO and AgO. If you heat it alone, if you go to the market and you bring silver oxide, if you go to the market and you bring mercury oxide and you heat it, it will give you, look at this everybody, if you heat it, it will get converted. It will get converted into what? Oxide form will be reduced to mercury. Mercury oxide will get converted into mercury. But if you bring from the market, that is Cu2O, then you need a reducing agent. But in this case, here we don't require any external reducing agent. We don't require any external reducing agent. Here itself, this crushed ore behave as reducing agent. This Cu2S behave as reducing agent, and then it will gives you on heating, it will gives you Cu plus SO2 again. So here you see that in these metals can be reduced without any reducing agent, this copper and silver and mercury. But in case of copper, the crushed ore itself behave as reducing agent. If you heat alone this one, Cu2O, then you need at least carbon to reduce this one. This will help. But if you don't have the carbon, the crushed ore, for example, if we have this 10 particle of this one, and 2 are converted into this one. 2 are converted into this one. Then this will react with the 8 remaining 8 of this one. Then the 2 particle will react another 2 particle. Okay. And we can say that that instantly it is not going to convert first. It is not so happening that whole of the Cu2s will get converted into Cu2O first. No, step by step, some of the particle will get converted into this one, and then this will react with the unreacted this one, and this reaction proceed. So here we can say that in case of Cu2O, yes, Cu2s, crushed ore itself behave as reducing it. So note it down. Here the crushed ore itself behave as reducing. Note it down.
Yes, sir.
Yes. Ashwin, you were absent in the previous class.
Yes, sir.
Jobita, you were absent, and Abir was also absent, and Abir is not there. Still, Abir is absent.
Sir, I was present in the last class.
In the last chemistry class you attended, you attend in 9:30. I think so. Or you attended at the same time.
Sir, I attended in the same time.
But here I have written absent student. In your name is written absent. Do you join the late?
Yes, sir. I joined at 4:07 from my time.
Oh, you were late. That's why. Okay. So let me write the name who are present today. Okay. So note it down fast. Then Veda, Tejasvi, okay, and Abir. Okay. So note when you note this one, let me know. Okay. Done?
Yes, sir.
Yes, sir.
Should I move further? Okay. Let me explain you further. So now you know that in the case of calcium, in the case of copper oxide, the crushed ore itself behave as a reducing agent. Okay. So have you noted these two equations and all the equations? No. Now we shall be moving towards the smelting, means reduction with carbon. Okay. So the next step is the mid-reactive metals. These are called the mid-reactive metals. Okay. Zinc, iron. These are called the mid-reactive metals. Okay. Zinc, iron, tin, lead. So if they are having their oxides form, like zinc, ZNO, we have converted this one ZNO from, means ZNS has been converted into. So if I'm having this ZNS, like ZNS, when you heat it in the presence of oxygen, ZNS, when you heat it in the presence of oxygen, then it will get converted into ZNO plus SO2. And now further, like previously, if you continuously heat it, it cannot be reduced into Z. It will remain in Zn. It will not be going to reduce like Zn plus O2. No, it will not going. We need a reducing agent here. Okay, you understood?
Yes, sir.
So we need a reducing agent. So these are called the mid-reactive metals. And for these mid-reactive metals, we need some reducing agent. So we have Fe, Zn, Fe, tin, and lead. Okay. And this is carbon. Okay. And this one is carbon here. So carbon is more reactive than these all. So instead of using any element other than carbon, it will be costlier for us. So what we need to do here is we need to use the carbon, which is cheaper because we are studying the extraction of metals in the economical, because we are just studying the economical process where we can also convert ZNO by using another metal because it is a simpler displacement reaction. But here we are using only carbon because carbon is cheaper, and we are studying economical method that are suitable for extractions of metals. Okay, so if I'm using this one ZNO ore and then convert it with the help of carbon, then it will give you Zn plus CO2. If I'm having PbO, then it will give you carbon plus, sorry, lead plus carbon dioxide gas. Then again, if I'm having if I'm having iron, Fe2O3, then if I'm having this carbon, we heat it, we give you Fe plus CO2 gas. Okay, so this can be reduced with the help of carbon. Okay, got it? And this is called reduction with carbon, is called smelting. Okay, so reduction with carbon is called smelting. Note it down, please. Note it down, everybody. And when you're done, please let me know. Okay. So for multi-reactive metal, we use this.
Yes, sir.
Done, sir.
Okay. So note this statement also. The mid-reactive metals, metal oxide, can't be reduced by simple heating. They require suitable reducing agents for reduction, and reduction with carbon is called smelting. Note it down. Done?
No, sir.
Bit fast.
Noted, sir.
Okay. So let's move further, dear students. Now, if you know that these are the metals, okay, and you have seen this one, that the mid-reactive metals here, after the mid-reactive metals, we are having the two metals, that is aluminium. Before the aluminiums, we have magnesium, and chromium. Okay, so if I'm having manganese oxide, MnO2, and chromium oxide, Cr2O3. Okay, and these can be reduced with the help of aluminium. Okay, these can be reduced with the help of aluminium, and this is called aluminothermy. The reduction with aluminium is called aluminothermy. Let me write it. Reduction with aluminium is called aluminothermy. Okay, now you have seen that I'm just going to write it again. Sodium, potassium, calcium, magnesium, then aluminium, then chromium and manganese. Okay, and then carbon. So these metals are reduced with carbon, but you cannot reduce chromium oxide with the help of carbon, because chromium is more reactive than carbon. So chromium and manganese cannot be reduced. Yeah, chromium and manganese oxide cannot be reduced with the help of carbon. Okay, understood? Understood, everybody?
Yes, sir. Yes, sir.
So what we need is more reactive metal, this one, that aluminium. So if you are having this one and this aluminium and the powder of chromium oxide, Cr2O3, then it will gives you Al2O3, Al2O3 plus chromium in the liquid state. Okay, and similarly, this one also, that is manganese. If I reduce with manganese with aluminium, manganese oxide MnO2 with the help of aluminium, that will gives you Al2O3, Al2O3, Al plus manganese in the liquid state. Okay, this reaction is so exothermic that the heat liberated out during this reaction let the metal obtained in the liquid state. Okay, so because this reaction is so exothermic, it let the metal that is going to obtain manganese and chromium, it exists in the liquid state. Okay, got it? Got it?
Yes, sir. Yes, sir.
Yes, sir.
So as you know that I have written here that previously that this is the carbon, and carbon, below carbon we have zinc, then iron, then chrome, and then tin, and then lead. Okay, you know that we have written then zinc oxide, iron oxide, and tin oxide can be reduced with the help of carbon, because this carbon is written here. Okay, but you will be very much familiar that if we use aluminium and if we have Fe2O3, then it will get converted into Al2O3 plus Fe in the liquid state. Fe in the liquid state. Okay, and what is the use of this one? You know that very well that this Fe can be reduced with the help of Fe2O3. If we are having this with reacting this one with carbon, then it will gives you Fe plus CO2 gas. So it can also be reduced like this way. We have written here. So why we are using aluminium for this one? Can you give me this idea? An idea for this one? Here you see that this iron Fe2O3 can be reduced with the help of carbon. But here we are using this one for the reduction. We are using iron. Means when we are using aluminium for the reduction of iron, then Fe can also be obtained. Then why we are using this one? So this is specific reactions. Let me explain you that this is specific reaction. In this case, the metal obtained is not in the liquid state. In this case, metal obtained is not in the liquid state. Okay, and in this the metal obtained is in the liquid state. Metal obtained is in the liquid state. Okay, so what is going to happen here is that this is called thermite reaction, the reaction of aluminium with Fe2O3 to gives you Al2O3 and plus Fe in the liquid state. This is called thermite reaction. This is called thermite reaction. This is called thermite reaction, dear students. And this reaction is very famous, and it is used for joining the railway tracks and broken machineries. What we need to do here is, we have this railway track, for example. Okay, and these are the railway track. So what we do here, we just create a make a chamber like this. Okay, and we just fill here a powder of Al2O3 and Fe2O3 and powder of Fe2O3. Here is this powder mixture of Fe2O3 and aluminium and a burning magnesium ribbon is used here to initiate the reaction. When you mix it, reaction will not start. You have to initiate the reaction by using a burning magnesium ribbon. You take the burning magnesium ribbon and just put it, like you know that we use crackers, we fire crackers in the on Diwali, on some stuffs. Okay, so what we does, we start the reaction. Then once the reaction is started, then it will produce a large amount of heat. So similar is this process. When we have a mixture of aluminium and Fe2O3, and we start the reaction with the help of burning magnesium ribbon, then the reaction is start. And what is going to happen? This when this reaction start, this iron, which is the end product of this one, will get filled here in the liquid state, and this will fill this gap, and there is no need to heat the melter, because we cannot have everywhere furnaces to melt the iron. Okay, when we are joining the railway track, we cannot have every time the furnaces, the big furnaces, to melt the iron. We cannot heat it to that temperature. So we just use this reaction, and here the iron obtained is in the liquid state. So we are not going to use any furnaces. The only a magnesium burning magnesium ribbon is sufficient to give this amount of it. Oh, okay. So let me show you here if it is possible. Let me show you that how this thermite reactions takes place. Okay. So wait a minute. So now you can see here. So this one is obtained in the, so whenever we need a metal and we need metals in the liquid state, so we need these reactions. Okay. If we are having, for example, this is very spontaneous and fast reactions and large amount of heat is required. So when we are having this one, so this is called thermite reaction, and this thermite reaction is used for joining the railway tracks and broken machineries. Okay. You understood? Everybody in the class understood this one?
Yes, sir.
Yes, sir.
Okay, okay. So please note it down here that reduction with aluminium is called aluminothermy. Okay, this is also aluminothermy. If you are using aluminium as a reducing agent, then the reaction is considered to be as uh, is called aluminothermy. The process is called aluminothermy. Reduction with aluminium is called aluminothermy. But this reaction if you are using aluminium and Fe2O3. So this reaction has a special name and that is called thermite reaction. So if it is asked in the examination that what is thermite reaction, that you need to explain this one. That the reaction between aluminium and iron oxide to give liquid iron and aluminium oxide, that is called thermite reaction. So you can write it. Please note it down. The heat liberated out during the reaction let the metal obtain in molten form. Let the metal obtain in molten form. Okay. Done. Noted this one, dear students.
Done,
Done,
sir.
everyone. Okay. So let's move further. Now the next one is electrolytic reduction. As you are very much familiar that they are the metals that are above the chromium and aluminum. Like for example, if I'm having potassium, sodium, calcium, magnesium, okay, and there were aluminium, okay, then chromium and zinc. So here we up to this one we can reduce with the help of aluminium, okay, and this one we can reduce with the help of carbon, the mid-reactive metal with the help of carbon. And the metal that are below hydrogen, they can be limited with the help of just simple roasting. Now talking about these metals that are the top reactive metals or most reactive metals. So what we do for this one, for example, if I am having NaCl, so NaCl, this is an ionic compound and large amount of heat is being required to overcome the force of attraction between this Na and Cl. You cannot heat it because this is already a most reactive metal Na. So how can you, if there is no metal, such metal that can replace this one. And if there is a metal, so that can be also expensive metal. Okay. So you cannot use, means if you are having this NaCl, for example, potassium is more reactive this one. Then again, KCl will form and it will give you Na, and almost they have the same similarities almost, okay. So this reaction will be slow, not very spontaneous, because they have almost the same reactivity. And moreover, potassium is more expensive than sodium. So how can we use a more expensive metal to reduce the to reduce or to get the less expensive metals? So in this case, what we need to do here is we need the electrolytic reduction. What we do, we need to do the electrolytic reduction. Lytic reduction means in simple, we use electricity for this one. Okay, so let me explain you that what we do here, that for example, if you are having NaCl, sodium chloride, so we use molten NaCl. We just melt it in the liquid form. We heat it so much that it get melted, and then we pass electricity to it. On passing electricity, we get NaCl, Na solid, and Cl2 gas. Okay, so how can you get this one? If you are using this was as aqueous solution, for example, if I'm just using this one, don't get confused with if you are using aqueous. So this will become, this will go, if you pass electricity to it, then it will gives you chloralkali process. It will go to NaOH plus H2 plus Cl2. So this is chloralkali process that we have studied in the acid, bases and salts. Chloralkali process. So this, we cannot use this method to get the sodium because we cannot get the sodium. In order to get the sodium, we cannot use water, because if you use water, then it will gives you NaOH instead of giving Na. So if you want to get the pure sodium, then what you need to do is you need to heat this sodium chloride and melt it first, and then pass electricity to the chambers. That will gives you Na solid plus chlorine gas. Okay, so you cannot use aqueous in this one. Okay, understood everybody in the class? Abhi?
Yes, sir.
Yes, sir.
Okay. Okay. So we cannot use this one. Okay. So let's move further. And you need to note it down that what happens when if we are having this Na. Okay. So at anode, this is, that anode is positively charged and anode and cathode is negatively charged. Okay. So in the electrolytic cell, if we are having this positively charged rod and a negatively charged rod, this one is negatively charged and this one is positively charged rod, and this is anode, and this one is cathode. Okay, and we are just having this NaCl molten in this form. So when we have NaCl in molten state, then what is going to happen? At Na positive and Cl minus ion will be formed. Na positive and Cl minus ion will be formed because it is in molten state. So Na is positively charged ion, okay, and Cl is negatively charged ion. So what is going to happen? The two Cl minus ions will goes at because negatively charged, it will goes at anode. Okay, so at anode, the two negatively charged ion will go and they will lose their electron and will form Cl2 gas, because they are the two chlorine atom. 1, 2, 3, 4, 5, 6, 7. Chlorine generally have 7 electron in the outermost shell.
Yes,
2, 8,
sir.
7. But when it acquires one extra electron, is going to have Cl minus ion. And similarly, another one also 1, 2, 3, 4, 5, 6, 7, 8, and this is also going to have -1 charge. So in order to form chlorine gas, it must have 7 electron in their outer motion. 7 electron in their outer motion. And they should make a bond with sharing 1 electron like this, Cl2. This is Cl2. Okay. So here we can say that that the two electron will be loose by this one this one from this one, or one from this one, or one from this one, and they will give you 2 electron. So this will at anode. Anode, why anode? Because it is positively charged, and only positively charged rod receive the negatively charged ion. And what happened at cathode? At cathode, these two positively charged ion because you know that cathode is negatively charged and only sodium is positively charged, so it will goes to that one. Okay, so what is going to happen here? Na solid, sorry, Na positive ions, because you know that Na positive means it is going to have 2 8 electronic configuration, no with no charge, no with no 1 electron, and Na solid is actually 281. So it will must require 1 charge with 1 electron, so that charge will remove. So the 2 such ions will go and will require these 2 electrons, 1 each, and will form 2 Na solid. So the overall reaction for this one can be written as 2 Na 2 NaCl when in liquid state. When electricity is passed through it, it will gives you Na solid plus Cl2 gas, 2 Na solid plus Cl2 gas. Okay, you understood everybody? Understood everybody?
Yes,
So this is the reaction. So please note it down here. At anode there is always oxidation take place, and at cathode there is always reduction take place. Okay. Done.
Yes, sir.
Okay. So this is the electrolytic reduction. Noted down this one also. For example, in case of reduction of sodium chloride, molten NaCl is taken in electrolytic cell. When high current is passed through it at cathode, sodium ion get reduced to sodium solid. Note this reaction. While at anode, and note this one. Done, everybody? Dan, should I move further?
Yes, sir.
Yes, sir.
Abir, Ashwin, Shweta, Jobita.
Done, sir.
Done? Okay. And if we are having the if aluminum can also be used, means aluminum's oxidation can also be used. That means we can get the aluminum from the aluminum oxide by using this electrolytic reduction, same Al2O3. So when electricity is passed through it, then we use Al. We'll get Al plus O2 gas. Okay, so we can balance it. How many? 2, 3. You have to write here, multiply by 3. You have to multiply here by 2. So this is 2Al. Okay, so this is the reaction. This should be 4Al here. Okay, now it is balanced. So when you pass electricity again, then at anode is positively charged. So positively charged will get the oxygen gas, and then negatively charged cathode. This at cathode, this will be obtained. Okay, and so here we can have this equation. Just write down the equations only. Okay, of electrolytic reduction of aluminium. Write this one only. Done? Done, everyone? Shweta? Done?
Sir. No, sir.
Not at fast.
Done, sir.
Done, everyone. Okay. Okay. So now we have learned what we have learned, that the reduction today's we have learned that how can metals be reduced from their respective oxides. So we have learned that if we are having this HGS, Cu2s, or AGS, then these can be reduced by simple roasting. Simple roasting. Okay. And if we are having like iron, zinc, tin, lead, then this can be reduced with the help of, means if their oxide can be reduced with the help of carbon. And if we are having magnesium and chromium, manganese and chromium, then these can be reduced with the help of aluminium. We have learned about the thermite reaction. Okay, and that is used for joining the railway track. And if we are having more reactive metal like aluminium oxide, okay, and if we are having Al2O3, like if we are having KCl, NaCl, okay, KCl, calcium oxide, KCl, and NaCl. So these metals can be reduced with the help of electrolytic reduction. Lytic reduction. Okay. Now we have obtained the pure metal. If we are having Hg, then we HGS, then we have Hg. Sorry, Ag. If we are having HgS, then we can obtain Hg from this one. If we are having Fe2O3, ZNO, SNO, and PbO, then this can be reduced with the help of carbon, and we can get Fe, Zn, Sn, and Pb respectively by reduction of carbon from the oxide. Similarly, chromium and manganese oxide can be reduced with the help of aluminium, and these metals, the highly reactive metals, can be reduced with the help of electrolytic reductions. Now we have got the metals from their oxide if they are present in their oxide form, and if they are present in their chloride halide form, then they are also be separated out from their chlorine or iodine group by using simple electrolytic reduction. And now we have the metals, like we are having, if we are having copper sulfide, then we obtain it by simple roasting. We get copper solid. Okay. And if you are having copper solid, still it can have impurities. Not every atom of copper is of copper. It may contain some silver atoms, some gold atoms. So we are not just saying that it is not having impurities in the form of if I'm having copper atom. So if I'm not saying that it is going to have the impurities in the form of sand, no. Impure means anything that is present other than that metal. For example, if I'm talking about copper metal, so copper purity means that it must have all the maximum number of atoms as copper. It must not have silver atoms. It must not have gold atom. It must not have some other metals atoms. Okay. So purity means that 100%, 99.99% should have the same metals. Okay. So in the next class, we're going to study that how metals are refined. Okay. How their purest form, how can you get the purest form? We have gold 99.9% pure. So what is that and how we make them pure? So their electrolytic reduction that we're going to study, zone refining we're going to study in the next class, and we're just going to study the some types of ores, the names of some ores, and also the alloys. That most of the question is also being asked from the alloys. So that's all for today. We'll meet you in the next class. Okay, dear students. Okay.
Yes, sir. Okay, sir.
Okay,
Yes,
everybody.
sir.
That's okay. So that's all for today.
Thank you, sir.
Okay, take care.
Thank you, sir.